Thanks a lot.
Good.
Thanks a lot for inviting us to participate in your webinar and streaming conference. It is a pleasure for us to present what we have done and what we have published in this paper. We are from the University of Florence, and specifically from Visit Lab. Visit Lab means Distributed System and Internet Technology, or Distributed Data Intelligence and Technology Lab. We work a lot in the area of smart city and artificial intelligence and big data. I am the chair of the lab, and Enrico Collini is a student, is a PhD student for the national PhD course on artificial intelligence. Please, Enrico.
Okay, so this work was about developing a solution for predicting rainfall based landslides using explainable artificial intelligence solutions. Landslides are one of the major environmental hazards in the world, and based on these two studies, there is evidence that this is an important problem to assess. Providing accurate predictions, in our case 1 day in advance, could be extremely important for local authorities in order to manage these emergencies. The scenario based of this study is the metropolitan city of Florence, that has 41 municipalities, 1.5 million inhabitants, and the data history on which this work is based covers 341 landslides events. At the state of the art, the majority of solutions provide only susceptibility maps that are static features based, and you can compute them 1 or 2 times maybe per year. And our solution is a more dynamic one and can be used for early warning systems. It can send alerts for the municipalities and also develop dynamic hazard heat maps and can be computed daily. This is the overall architecture of the solution proposed, with the data acquisition, the development of the artificial intelligence prediction models, and also the outcomes that can be displayed in heat maps or alerts to the municipalities. We developed the data of the dataset using a grid composed by 1 kilometer per 1 kilometer square, obtaining this red region of the metropolitan city of Florence, better displayed in this image with the red dots that are the location in which the landslides occurred. And then our solution is innovative because it uses both static features but also dynamic features like the temperature and the rainfall values. The data are acquired by sensor located in the territory, and these values have been interpolated by using the inverse distance weighting interpolation algorithm. So we compared some of the most used artificial intelligence architectures based on the state of the art in order to provide the prediction for the next day. The resulting best architectures is the extreme gradient boosting machines that has been trained with almost 9 million data that achieves astonishing results like an accuracy of 0.99 on the prediction of the landslides. Compared to the system that is the Sigma, that is used right now, that was used for the Tuscany region, in which Florence is, that has instead lower values like the the false alarm that was really high, and instead in bold we can see that our solution is better performing for the okay.
Yes.
So
yes.
We added the explainability to our artificial intelligence model, and in this you can see which are the most important variables, like the T3, that is the rainfall accumulated in the last 3 days. We used these sharp values to understand more the impact of these features, and in the graph on the right we can see the impact of the sharp values. The reddish color means that high values of this feature contribute to the prediction of the landslides. As you can see, this one is a really important one. The water level in the soil, that when there is a lot of this, it's probable that it will fire a landslide. Or also the free, that if it is not rained a lot in the last 3 days, it is probable that the landslides will not occur. So this is important. High rainfall values associated with also high temperature and high levels of water within the soil have the main correlation with the prediction of landslides events. Our goal was to use these explainable results to develop early warning system. In more details, we also investigated the local event. In this picture, you can see 3 cases, A and B, in which a landslide occurred, and the last one in which the landslides did not occur. These local explanations puts in evidence that which are the features that provided the major contribution to the prediction of the landslides. For example, in the first one, we have the free, max temp SIR, humidity, and in the third one, we can see which values of this sharp contributed majorly to the not prediction of the landslides. This is a better graph to show, because it contains the trend of the sharp values of these features that are the most important ones, and in this date and in this place in which these sharp values are based, occurred a landslides. As we can see, we have levels here Hydra that fired a big sharp value, also day 3 with a big sharp values, and this max temps here that fired a high value. So based on these sharp values, we can develop a warning system 1 day in advance, provide municipalities with alerts, and also build dynamic hazard heat map. We can say that this solution is robust because in this graph you can see the relation that a particular feature has with these sharp values, and in this case, day 30, that is 30 days of rainfall accumulated, when this feature has a value of around 120, the sharp value is really high. So in this case, it is probable that it will fire an alert, maybe about a landslide somewhere in the scenario studied.
Okay, so as a conclusion, the problem, so we addressed the problem of landslide having prediction, and with the aim of creating an early warning tool for the metropolitan city of Florence, which is an area of 1,500,000 inhabitants lives. So we use the static land description features and also dynamic features as rainfall, temperature, wind, and so on. Dynamic features just estimated in the last days and in the previous days, but continuously updated every day. So we also tested a large number of artificial intelligence solutions to compare them and to get the best performing architecture. We identified the XGBoost to be the best for the TSS metric that has been listed in the comparative table before. So regarding the explainable AI, we adopted the Shapley additive explanation, the so-called SHAP, for global and local explanation. Global means to estimate the global relevance, and local to provide at the decision makers for each event the rationale behind the defining condition for the early warning. And most of the case, the responsibility was identified to be assigned to the rain condition in the last 3 days, and the max temperature in the previous day, and the level of water in the river. The most relevant for static features were the precondition for landslide are not so they were identified, while they are not sufficient in creating an early warning system. So to use the landslide, the land features, land static features is not enough to make prediction. It's enough to make a susceptibility map, but not to make prediction. So from the computational point of view, the prediction can be assessed every day for a large area like so with close to 4,000 points is quite viable. It could be computed even for the whole Italy with enough computational capability. So this is much more expensive than estimating the susceptibility map that is typically computed 1 or 2 times per year. And so prediction model can be used to prevent a disaster 1 day in advance, and that can be used to inform the population what could happen to create some alarm and early warning. So the paper has been published on IEEE Access this year, so you can get the link from the program and also here. And so is the general idea in our application and in the infrastructure that is called the Snap for City, that covers the Florence area and many other areas, is to ingest the data, aggregate, perform data analytics, and provide rendering of the many conditions and create a decision support system. So the work has been developed in the context of instrument for the resilience of the risk assessment and resilience of the area, and for providing decision support system. So as in the schema that you see here in the right side, to have a short-term prediction, anomaly detection, and the long-term prediction to provide recommendation and prescriptions that could be used for early warning and for the what-if analysis. The whole infrastructure, as I told you before, is based on Snap for City framework, that is a fully open source infrastructure and tools that you can download and install. And they are used by us, but in many cities of Europe, it is also installed and used to make smart city activities, but also for early warning or just for smart parking, smart light, smart waste, or others application. And also by the European Commission is also use this tool. In the infrastructure, you can have any kind of data, not only the data that we have adopted for the landslide prediction model, but also maps of any kind, synopsis, trajectories, traffic flow, 3D reconstruction, beams, and others. Data. If you are interested, you can go in this link to get a training course for all the experts. You can test the infrastructure. You can free register it on www.stratfordcity.org. You can go inside and test and see what you can do. You can download technical documents, flyers, and technical overview of the platform. Thanks a lot for your time and to give us the opportunity to present our work in this prestigious forum. Thanks a lot.